As long ago as the year 1793, the Italian Lazzaro Spallanzani discovered that blinded bats were able to avoid obstacles when flying. A Genevan scientist, Louis Gerine, found soon after this that bats with obstructed ears were unable to do so. Both scientists concluded that hearing was important in nocturnal bat flight, but could not explain why. Their work was disregarded and fell into oblivion, but in the early part of the 20th century, it was suggested that high-frequency sounds were involved, and the development of sufficiently sensitive apparatus enabled an American scientist, Donald Griffin, to establish in 1938 that this was so. Almost coincidentally, the Dutch zoologist Dijkgraaf arrived at a similar conclusion after studying the faint sounds sometimes heard when bats are flying, but it was not until the Second World War ended that his work became known. Most of the sounds are ultrasonic, and therefore beyond the normal range of human hearing of 20 Hz to 20 kHz. Most echolocating bats use frequencies of 20 to 80 kHz, but some range as high as 120 to 210 kHz. Only microbats use high-frequency echolocation for navigation, hunting, and catching prey. The sounds are produced in the larynx and emitted through the mouth or through the nostrils, in the case of bats with nose leaves, the leaf apparently serving to modify, focus, and direct the beam of sound. Echoes received by the ears provide information that can be processed by the brain to provide the bat with an interpretation of its surroundings and the location of flying or resting prey. The megabats lack echolocation of this type, but a few species of fruit bats produce orientation sounds that are partially audible, 5 to 100 kHz, by clicking the tongue. Unlike other megabats, these bats roost in the darker parts of caves and use this form of echolocation to navigate in and out of the caves, though they orientate visually in better light. The ultrasonic pulses vary in duration from about 0.2 milliseconds to 100 milliseconds and may incorporate from 1 to 5 harmonics or overtones. By human standards of loudness, the sounds may be very powerful and of high intensity. Frequency-modulated signals sweep in a shallow curve or sharply through a range of frequencies, usually downwards. Other signals are emitted at a constant frequency. Most bats vary their acoustic repertoire, using both FM and CF patterns in varying degrees and combinations. Some use CF signals of moderate to long duration to establish target movement and speed by means of frequency changes in the echo called Doppler effect. Typically, a hunting bat will search using an emission rate of 5 to 10 pulses a second. Once a flying insect has been detected, the pulse rate increases to 15 to 50 a second, this approach phase being terminated by a stage in which the pulse rate may reach 200 pulses a second, this high rate providing the bat with continuous information about the target. Some moths have a simple ear on the thorax that can detect bat echolocation sounds, and so warned, these moths are able to take evasive action. Other moths produce a train of ultrasonic clicks that mimic bat calls and so interfere with the bat's echolocation system. On the other hand, some long-eared bats can locate their prey by listening for its sounds. Certainly, the fringe-lipped bat is quite adept at discerning the social calls of the pond frogs that it hunts. Megabats also produce low-frequency audible calls of many kinds. The epauletted fruit bat honks metallically during the night, and male hammer-headed fruit bats produce low, throaty, and intense metallic calls to attract females. Squeaks, squawks, and screams in the roost or around a fruiting tree may express annoyance or disputes over space. Pulses of ultrasound emitted by a bat spread outward from its head like ripples in a pond. The strength of the reflected vibrations gives information on the distance of the prey, while slight differences in the time taken for the reflections to reach each ear give information on its direction. Pulses of ultrasound are often complex. The sequence begins with a series of constant tones, each of which glides rapidly to a lower frequency through about a quarter of an octave. As the bat homes in on its prey, the pulses are emitted more rapidly, their frequency increases slightly, and the constant tone almost disappears. To be able to chase and capture a moth in the dark seems an astonishing feat. Even more remarkable is the fact that the bat simultaneously recognizes all the other objects in its vicinity: the ground, trees, bushes, rocks, other bats, and owls. It sees by means of ultrasound.